Hello, my name is Shawn Lim, and this is my candidate presentation on field-driven dynamic charge stability of nitrogen vacancy centers near diamond water interfaces. So, what material are we studying? Diamonds are known to be the hardest known material, typically seen in jewelry. But did you know that diamonds can range in a wide variety of colors? In the molecular scale, these colors are explained by quantum defects in the diamond lattice that make up localized energy bands that change what wavelengths the material can absorb. For example, a defect consisting of a substitutional nitrogen atom, a vacancy right adjacent to it, and a negative charge localized to its effect emits a pinkish reddish diamond color. This configuration, known as the nitrogen vacancy center in diamond, is a popular quantum defect known for its high spin coherence times in room temperature. Due to its sensitivity known into phonon vibrations, this defect can play into technological applications like qubit systems for quantum deep computing, thermometers, and quantum field sensors, specifically underwater biosensors. Now again, NV sensors are really sensitive. The problem with using NV sensors in aqueous environments is that water molecules have their own dipole-induced electric noise that perturb these effects. The aqueous noise decreases spin coherence times and can also act as a location for electrons from the NV pair to delocalize towards. Experimental studies have shown that electrode stabilities can be enhanced by an external electric field induced by an electrochemical cell. However, these experiments are costly and require unconventional equipment in cryogenic or isolated settings. Only exclusive labs can afford enough diamond samples to test for this experiment in particular. This calls for demand for computational methods involving first principle calculations, methodologies like density functional theory or ab initio molecular dynamics. This not only cuts costs, but also explains atomistic scales explanations for experimentally observed phenomena. So in my research, I present a computational study of negatively charged nitrogen vacancy center in aqueous environments. I built a diamond water supercell and integrated a computational potentiostat that combines atom fluctuations and electric field and temperature-induced fluctuations all at once. Atom behaviors, spin states, electron orbitals, and band structures are observed for several picoseconds. Density functional theory-based calculations demonstrate an electrodynamic barrier decreasing after applying an electric field, explaining likelier electron transfer from the solvent to the diamond. So with these results, I hope that this study can influence quantum material simulation and mass production of NV centers, aiming to provide insight to nanoscale materials even without a microscope. Thank you.